This is 2015, number 4. It says consider the differential equation dy dx equals 2x minus y. This is called a slope field. It might look unfamiliar to you, but it's called a slope field. This is going to be one of the last things we do in the year, so we'll push that off until then as well. We can actually do part B in this one. It says find d squared y dx squared in terms of x and y. So we're already given the first derivative, dy dx. They want the second derivative, d squared y dx squared. And they want us to write it in terms of x and y. So when we find the derivative, we'll do that. It says determine the concavity of all solution curves for the given differential equation in quadrant 2. So we need to know the concavity in quadrant 2 and give a reason for your answer. So let me just rewrite this part down here. So part B says dy dx equals 2x minus y. So the first thing I want to do is find the second derivative. So the second derivative is the following. D squared y dx squared equals the derivative of 2x with respect to x is 2. The derivative of y with respect to x is dy dx. So be careful because it says in the directions find d squared y dx squared in terms of x and y, not in terms of dy dx. So we are not okay to leave our answer like this with a dy dx in the answer. So instead, let's replace it with what dy dx equals. So I'm going to plug that into this function. So d squared y dx squared equals 2 minus, and then watch that I'm going to put this in parentheses because I don't want to forget to distribute that negative. 2x minus y. And if I distribute the negative then, I get 2 minus 2x plus y. So here's my answer to the first part. D squared y dx squared equals 2 minus 2x plus y. The second half of this says determine the concavity of all solution curves for the given differential equation in quadrant 2. The wording of that might not make a ton of sense, but you know how to find concavity. You know that if the second derivative is negative, it will be concave down. If the second derivative is positive, it will be concave up. And they're only looking in quadrant 2. So let's see what type of numbers we have in quadrant 2 on an x and y axis. These are the positive x values. These are the negative x values. These are the positive y values. These are the negative y values. So here, both x and y are positive and positive. Here, they're negative and positive. Rewrite that. Negative and positive. Here, they're both negative. And here, they're positive and negative. So with that said, in quadrant 2, the types of numbers I'm looking at are negative x values and positive y values. So let's see what happens if I plug a negative number into here. So let's just look at this piece right here. Alright, I have 2 minus. If I plug in a negative number here for x, because again in quadrant 2 all my x values are negative, if I plug in a negative number here for x, I have negative 2 times a negative number, that's a positive number. And then y is also a positive number because in quadrant 2 all the y's are positive, so that's another positive number. So I have 2 plus a number, that has to be a positive number. And if that's a positive number, then what can I infer about the concavity of the original function? I can infer that the concavity would be concave up. So a good justification would be the following. It says determine the concavity for all solution curves of the given differential equation in quadrant 2. You can write all solution curves are concave up in quadrant 2 because, and here's where the justification part comes in, our reason is because the second derivative is always positive. In quadrant 2. And on the AP exam, that answer is worth 2 points. And the other parts of this question we're not able to answer yet. We don't know how to find a particular solution, and then we don't know how to find the constants yet for the solution to the differential equation. So we'll wait on those 2 parts until second semester.